Modern software is no longer constrained by human-written rules. Instead of executing explicit instructions, today's artificial intelligence learns entirely from examples. By processing massive datasets, the system iteratively adjusts billions of its own internal mathematical parameters to recognize complex patterns. This transition from hard-coded logic to iterative parameter optimization is the engine driving modern AI. This diagram shows the core architecture of an AI model, the neural network. It is organized into an input layer, hidden processing layers, and an output layer. Looking closer, this illustration breaks down a single node, or neuron. Each neuron acts as a mathematical operator, applying specific numerical weights and a bias to incoming data. Calibrating those weights requires an immense scale of information. Frontier models now process tens of trillions of data tokens. That data is fed into the system in two primary ways: supervised learning using labeled examples, and unsupervised learning using raw, unlabeled text or images. The architectural depth of the network, combined with the sheer volume of its training data, strictly determines the model's baseline capability. The training cycle starts with a forward pass. Raw data moves through the network layers to generate an initial prediction. Next, the system uses a loss function. This mechanism compares the AI's prediction against the correct answer to calculate the exact margin of error. This chart illustrates the backward pass, or backpropagation. The system calculates how much each individual weight contributed to the error, adjusting them to move down the gradient toward the global minima. This visualization demonstrates a critical risk. While adding more hidden layers increases a model's representational power, it introduces overfitting, where the network memorizes the training data instead of learning general patterns. To prevent this, engineers use techniques like dropout, randomly deactivating specific neurons during training to force the model to generalize. The entirety of AI training is a non-convex mathematical optimization problem, dedicated strictly to minimizing predictive error over millions of iterations. Once the internal weights are locked, the training phase ends and the model enters inference. When a user submits a prompt, data flows through the static network to calculate output probabilities for the next token. A temperature hyperparameter alters this. Values under 1 create predictable outputs, while values over 1 flatten the distribution, introducing creative variance. Regardless of how human-like the output appears, generative AI is ultimately executing sophisticated, large-scale statistical probability matching. An AI model's final reliability is directly proportional to two physical constraints: the quality of the ingested training data and the sheer computing hardware dedicated to optimization. Flawed, biased input data permanently degrades the internal parameters. Rigorous data curation is what yields highly capable, trustworthy AI inference.